Hello everyone, welcome to the video. Today we are going to solve the problem 01 knapsack problem. In this problem, we are given n items and every item carries some value. Every item also carries some weight. So for all the n items, we are given the value that it carries and the weight that it carries. Now our job is to pick some of these items and put them in a knapsack. But we want to pick the items in a way that we maximize the value that we have picked. But there is a constraint. The constraint is in terms of the capacity of the weight that the knapsack can carry. So, this is the problem that we have a fixed capacity that the knapsack can carry. We have n items with their values and weights. We have to return what is the maximum value that we can put in the knapsack within this capacity. In the previous video, we had solved this problem using top-down dynamic programming approach. In this video, we will be solving this problem using bottom-up dynamic programming approach. Here, we will also see the space optimization of the bottom-up approach. We are going to solve this problem today. We will go through the thinking process, we will write the algorithm, and then we will also see a working code for the same algorithm. Later, we will also see an extension to the problem. The extension being that we have to also return the items that we have picked and not just the maximum value that can be achieved. So before we start, if you are new to this channel, please don't forget to subscribe and press the bell icon. Let's start. To begin with, let us first note down the key things given in the question. We are given that there are n items. Each item carries some weight and each item carries some value. The weights and values of these items are given to us in terms of array. Now what we have to do, we have to put some of these items in a knapsack. But there is a constraint. The knapsack has a limited capacity of W in terms of weight. So we cannot exceed this capacity when we put some of these items in the knapsack. So what do we have to do? We have to return what is the maximum total value that we can make in the knapsack under this capacity. So if we consider an example, we have 3 items. Each of them has weight 1, 1 and 1. But the value of each of them is different, 10, 20 and 30. Now in this case, if our capacity is 2, what is the maximum value that we can make? We can make 50 by picking up these 2 items, one with value 30 and one with value 20. So if we consider our solution as a black box, we are getting as input what are our number of items, their values, their weights and the capacity of the knapsack. And what do we have to return? We have to return the maximum value that we can form. So what will our function signature look like? Our function signature will look something like this. Before moving to the bottom-up approach, let us first briefly recap how did we solve this problem using the top-down approach. First of all, we made an observation. We thought that whatever combination of items leads the maximum value, that combination of items will either contain the last item or it won't contain the last item. That was a fair statement to make. From that, we thought that we can first compute the maximum value that we can obtain by including the last item. Then we can compute the maximum value that we can obtain by excluding the last item completely. And then whatever is the maximum of the two will be our answer of the maximum value that we can obtain for these items. Then we went on to further analyze the include case. We thought, let us include the last element and let us try to figure out what will be the maximum value possible formed. So since we have included the last element's value will definitely be included. In that, what we need to add is the maximum value that we can obtain using remaining elements for the remaining capacity. So if we were considering for our original problem that we have I elements and we have J capacity,
the remaining elements became the first I minus 1 elements only, because the last element is already taken. And remaining capacity became J minus the weight of the last element. So this became the answer for our include case. And if we were to exclude the last element, that means our problem became that we have to find the maximum value to obtain by using only first I minus 1 elements and the J capacity. So we could see that our exclude answer will be knapsack of I minus 1 and J. Here what we had done was we had expressed our original problem in terms of answers of our smaller problems. That means we were using recursion and we were able to successfully derive the answer for original problem using answers for smaller problems. So this was our recursive relation. Now, as with any recursion problem, we were going through step by step. We had already done the first step of identifying the recursive relation. We also had identified the inputs that would go into our recursive method. This was our recursive method call. It took as input I, which denoted that we are considering first I items. It took another input as J, which denoted the capacity of the knapsack. And other two inputs were weight and value arrays, because we needed them to calculate last element's value and last element's weight. We first tried to convert this recursive relation into algorithm. So we knew that we needed last element's value and last element's weight. So we first tried to calculate that. Now if we were considering first I items, the last element would lie at index I minus 1. So we could get the values of the last element value and last element's weight. Next we wanted to calculate the answer for include case. But include case made sense only when the capacity of the knapsack was greater than the weight of the last element. So we added this condition. And in this condition, the include answer was the value of the last element plus the maximum value that we can achieve by remaining elements, the I minus 1 elements with the reduced capacity. The reduced capacity being J minus the weight of the last element. And we still passed weight and value to this same recursive method call. Else, if the weight of the last element was greater than the capacity, then it did not make sense to compute the include answer. So include answer was 0. And if we had decided to exclude the last item, then that meant we have to maximize the value formed using first I minus 1 elements and our capacity using J. So we called this same method with these inputs and got the exclude answer. The maximum of the two was our current answer and we could return that. But this algorithm in itself was incomplete, as it would go into infinite recursion as this method kept on calling itself. To terminate this infinite recursion, we needed something called as base or terminating condition. Now the base or terminating condition is usually reached when the input to the recursive call is the smallest. We had two inputs, the number of items and the capacity. So we thought that what is the minimum number of items that we can reach. Since I was getting reduced by 1 in every step, we thought that it is possible that I reaches 0. Now I being 0 meant there were no items to pick. Therefore, the maximum value that can be formed was 0. Now the J was the capacity. This J was getting reduced by some random weight in every recursive call. But we made sure that J always stayed positive. If the weight of the last element was greater, we did not reduce J. Therefore, at max, J could have also reached 0. And what does the value of J equal to 0 signify? It means that the knapsack does not have any spare capacity. In that case, the maximum value that we can form using these items will again be 0. Now this was a complete algorithm, but it had very high time complexity. It had many overlapping problems. But we could solve the problem of overlapping problems by using a map. We stored the answers for for every combination of I and j in this map. So whenever we encountered an input, we first checked if we had encountered this input before by checking if the key was present in the map. If it was, then that means we had already calculated the answer for that pair of I and j. So we returned the answer directly from the map without going through this calculation. And we could do that because before returning the answer, we would first store it in the map against this key. So this completed our top-down dynamic programming approach to this problem. The next step was thinking bottom-up. But why was the bottom-up approach required? What is the problem in top-down dynamic programming approach? The problem is recursion. Every method call occupies some space in memory. And with recursive methods, as the recursion tree grows larger, the number of method calls increase. That means a large space is consumed in the memory. We don't want that. Ideally, what we would want is we could solve the same problem in the similar time and space complexity, but without such large number of method calls or without using recursion. And that is why we need to think of bottom-up approach. What do we mean by bottom-up approach? In top-down approach, we start by calling our recursive method with the largest inputs that are given to us in the problem. Then, as the recursion progresses, our inputs to the recursive call become smaller and smaller till we reach the base conditions. In bottom-up approach, we do it in reverse. We first calculate the answer for smallest inputs or for our base conditions and then gradually build on top of it. We move upwards towards larger and larger inputs till we reach the situation where we have the answer for the inputs that were asked in the question. In bottom-up approach as well, we use the insight of the recursive relation. We will still use the answers of smaller problems to derive the answer for our larger problem, but we will do this in reverse order. That means even for bottom-up approach, we still need to store this information that for a pair of I and j, this is our answer. We need to store this information and we need to be able to iterate from smaller ij's to larger ij's. What data structure would suit this the best? We can use a two-dimensional array. The first dimension can correspond to the number of items that we are considering, and the second dimension can correspond to the capacity of the knapsack. The number of items that we are considering can range from first 0 items to first 1 item to first 2 items and so on till first n items that are given in the question. The capacity can range from 0 to 1 to 2 and so on till w that is given to us in the question. So what will be the dimensions of this two-dimensional matrix? It will be n plus 1 into w plus 1. Now let us see what does any position I, j mean in this matrix. This position means that we are considering first I items from the items given in the question and the capacity of the knapsack is j. What will the value at such a position signify? The value here will signify the answer. That means the value here will tell that what is the maximum value we can make by picking some items from the first I items with capacity of the knapsack being j. So if we have this matrix filled completely, can we have our final answer? Yes, our final answer will correspond to this position. So we have noted here that our final answer will be dpnw. Okay, so now we have to find a way to fill this matrix. Let us see how will we fill the value at any position I, j. Now to fill value at any position I, j, we need the value of last element. Now since we know we are considering the first I items, we will know the value of last element as the element at I minus 1th index. Similarly, we will know the weight of the last element. Now, what we need to do? We need to find answer for this combination, I minus 1 and j minus last element's weight. Now, I minus 1 means answer in the previous row, and j minus last element's weight means answer in any of these prior columns. Let us say it corresponds to this element. So, the value that we will fill here will depend on the value here. Similarly, for exclude case, we need the answer for the combination of I minus 1 and j, which corresponds to this position. So, the value that we will fill at this position I comma j will depend on the values here and the last element's value and weight. So, if we had filled this matrix row wise, then by the time we reach here, we will already have the values here. So, we can fill this value. That means we should fill this matrix row wise. Okay, so now we know that we have to fill this matrix row wise. We know how to fill the value at any position I comma j, and we know that if we have filled all of these values, what will be our final answer. The only question that remains is how do we even begin to fill this? As discussed earlier, we will begin filling this from smallest input or our base conditions. And what do our smallest input mean? Our smallest inputs mean I is equal to 0 and j equal to 0. I is equal to 0 corresponds to the first row, and it also means that we have no items to pick from. That means the values here will be 0. Similarly, j is equal to 0 corresponds to first column, and j is equal to 0 also means that the knapsack does not have any more spare capacity. Therefore, the values here will also be 0. That means now we know how to begin filling the matrix, how to fill the value at any position in the matrix, and once all the values are filled, where is our final answer? So we have everything that we need to convert our thoughts into algorithm. So let's try doing that. We clearly need a two-dimensional array of the size n plus 1 and w plus 1. We will fill its first row with zeros and its first column with zeros. Next, our aim is to fill the whole matrix. So we will iterate. We will iterate for I is equal to 1 till n and for j is equal to 1 till w. Now we are at any position I comma j, and our aim is to fill the value at that I comma j. To fill the value at any I comma j, we need to first fill the include answer. For include answer, we need the values of last element val and last element weight. Now, if we are considering first I items, at what index will the last element lie? It will lie at index I minus 1. So we have the last element's value as val I minus 1 and the last element's weight as weight I minus 1. Now we need to fill the value for include answer. Now, to go for include answer makes sense only if our current capacity j is greater than the weight of the last element. So we add this condition that if j is greater than equal to last element weight. Now in this case, what will be our include answer? Our include answer will be last element's value plus the value for the combination of I minus 1 and j minus last element's weight. How can we get this value? It will be present in our matrix at this I and j. So here we get our include answer. But this is the include answer if this condition is satisfied. If this condition is not satisfied, meaning the weight of last element is greater than our capacity, then it doesn't make sense to include the last element. Therefore, in that case, we make include answer equal to 0. Now we have to look for the answer for the exclude case. The answer for exclude case is denoted by this expression. That means we will find the exclude answer at this position in the 2D matrix. So we will have the exclude answer as well. Now we have to get the maximum of the two and put that in our dpij. So we take the maximum of the two and put that in dpij. This way we can fill the values at dpij and we can fill the whole matrix. When we are done with all the iterations, our final answer will lie at dpnw. This completes our bottom-up dynamic programming algorithm for the knapsack problem. What will be the time and space complexity of this approach? Since for every combination of n and w or I and j, we are calculating the answer once. Therefore, the time complexity is big O of n into w. Similarly, space complexity is big O of n into w because of this 2D matrix that we are using.
Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function. It takes as input the number of items n, the capacity of the knapsack w, and the weight and the values of arrays. Weight and values array. It is supposed to return the maximum value that we can carry in the knapsack with the capacity w. So first of all, we declare this 2D matrix of size n plus 1 and w plus 1. Then we fill first row with zeros. First row means I is equal to 0 and I is equal to 0 means there are no items to pick from. That means we cannot take any value. So we fill the first row with zeros. Then we fill the first column with zeros. First column means j is equal to 0. J is equal to 0 means the knapsack does not have any capacity. That means that the maximum value that we can take is 0. So we fill the first column with 0. Now our aim is to fill the whole of the matrix. So we have to iterate. We will iterate for I is equal to 1 to I is equal to n, and from j is equal to 1 till j is equal to w. Now we are at any position I, j and we want to fill the value here. To fill the value here, as per the recursive relation, we need the values of the two things, last element's weight and last element's value. Now, if we are considering first I items, then where at what index will the last element lie? It will lie at I minus 1. So we get the last element's weight from weight array at I minus 1 and we get the last element's value from the value array at I minus 1. Now, using this, we want to calculate what is the answer for the include case. What is the answer for the case when we include the last item? So it makes sense to include the last item only if the capacity of the knapsack is greater than or equal to the last element's weight. So we add this condition. And if this condition is satisfied, then the maximum value that we can take is the last element's value plus the value for the combination of I minus 1 and j minus last element weight. Why do we say that? Because now the smaller problem is that we have to maximize the value using first I minus 1 items and with the remaining capacity as this. So we can get our include answer. But if this condition was not satisfied, if the last item's weight was greater than the capacity of the knapsack, then it would not make sense to include that item. So include answer will be 0. And exclude answer is pretty simple. Exclude answer means that we don't have to take the last item at all. That means we have to maximize the value that we can find, that we can make using first I minus 1 items and with the capacity j. We can find this value at dp I minus 1 j. Now we have include answer and we have exclude answer. So our answer for I, j is the maximum of the two, and that is what we fill the dpij with. This way we can fill for all ij. That means we can fill the whole matrix. Once we are done filling the whole matrix, our final answer will lie at dpnw and we will return that. So this is the code for the bottom-up dynamic programming approach for the knapsack problem.
So far, we have focused on finding the maximum value that can be made using items in knapsack. But there could be an extension to the problem as well. Instead of returning just the maximum value, we could be asked to return the actual items that make up the maximum value. For example, here in this case, the items at index 1 and items at index 2, these two combined make up the maximum value 50. So we could be asked to return a list of 1 and 2. How do we solve that? Let us see if we can extend our algorithm to find the actual items in the knapsack that make up the maximum value. In the algorithm, we know that for any combination of I and j, we choose one of the two. One, either the include answer or the exclude answer. Include answer means we have included the last item, and exclude answer means we have excluded the last item. That means for every I, j, we know whether we have included the last item or not. This gives us a hint that we can probably trace the items that make up the maximum value in the knapsack. Let us say we had some way of storing this, that for a combination of I and j, whether we have included the last item or we have not included the last item. We can use a two-dimensional array to store this, just like we used a 2D array to store the results for every I and j. Let us say, while going through the algorithm, we have both these 2D arrays filled. Both of these 2D arrays will be of the size 4 cross 3, n plus 1 cross w plus 1. All of these positions will be filled, but here, for the example's sake, we have filled only a few positions. Now let us see if it is possible to use the values of this results matrix and the values of this include-exclude matrix to derive what were the items that we used. So our problem was about n is equal to 3 and w is equal to 2. So n is equal to 3 and w is equal to 2 corresponds to this position. At this position, we can make the maximum value as 50. And from the algorithm, we will know that we have included the last item. The last item meaning the third item. So we can put this index and store it somewhere. So we have stored this 2 here. Now, since we are in the include case, we have preferred the include case at this position. What is the smaller problem that we need to go to? Since we have included the last item, now we have to deal with first 2 items only. And the remaining weight is the original weight minus the last element's weight. So the remaining weight is 1 and we have to deal with first 2 items. So we are dealing with position 2, 1. Now at 2, 1, it is possible to make the maximum value as 20. And to make the maximum value at 20, we will know from the algorithm that we will have to include the last element. Last element meaning second element. So we will again note the index of this second element and store it in our storage. So we have stored 1 here. Now since we have included the second element as well, now we have to maximize the value using only first element and the remaining weight as 0, since 1 weight is consumed by including the second element. So we have to go to the position 1, 0. Now at 1, 0, it is not possible to make any value further. So we don't need to, that means we won't need to include any more items. So the items that we included in the knapsack for maximum value are here, 1 and 2. So we can see that we can use these 2 matrices to derive what are the items that we put in the knapsack to obtain the maximum value. So let us now try to formalize our thoughts into an algorithm. So we are clearly iterating, and we are iterating till where? Till the maximum value we can form becomes 0. And in every iteration, what all information do we have? In every iteration, we know what is I, that is what are the first I items that we are considering. We know what is j, the capacity of the knapsack. What is the maximum value that we can obtain for this combination of I and j? We can get that from the results matrix. We will know what is the last element. If we are considering first I items, then the last element lies at the index I minus 1. And we know whether the last item was included or excluded through this matrix, include-exclude matrix. Our aim here is to figure out the items that are included in the knapsack. So for this I, j, we will first check if the last item was included. We can easily check if the last item was included using this 2D matrix. If the item was included, we have to include that index in the list of items. So we will push that in the stack. We are using stack here because we are getting the information about later elements first. So we put that in the stack. And then we know that what will be our subproblem. And for the subproblem, we will update our I and j accordingly. Else, if the last item was not included, then again we will update our I and j accordingly. We will continue iterating it till the max value becomes 0, and then we won't go into this loop. Then in such a case, in the stack, we will have the items or the indices of the items that were used to obtain the maximum value at this initial I, j. We can then convert this stack into list and return. Now the only thing that remains is how do we fill this matrix. Filling the include-exclude matrix is pretty simple as per this algorithm. We will know whether the include answer was greater or the exclude answer was greater. If the include answer was greater, put the value as 1 against that I, j. And if the exclude answer was greater, put the value as 0 against that I, j. In this manner, we can return the actual items in the knapsack that make up the maximum value. So this completes the extension part of our problem as well. Let us now come back to our original problem, where we were focusing on returning the maximum value that we can obtain and not on the items, returning the items that make up the maximum value. There could be an extension to the problem here as well. We could be asked to optimize the space complexity. Now in our previous solution, our space complexity was big O of n into w because of this two-dimensional matrix that we were using. Let us see if we can reduce this further. Let us see that do we need this whole of this matrix at any point in the algorithm. Let us try to see what all do we need when we try to fill the value at I, j. As per this recursive relation, we will need the value at this I minus 1, j minus something. Now where will this lie in this matrix? I minus 1 means previous row and j minus last element weight means any column prior to this. So maybe we can consider that this is lying here. We also need the answer for position I minus 1, j. Now where will this lie in the matrix? This will lie in the previous row right above it. That means to fill the values at I, j, we need the values from the previous row. We also need the last element's value and the last element's weight, but for that we already have the weight array and the value array. And here to fill the value at I, j, we only need the values from the previous row. That means there could be 1,000 rows above this row and we won't care. We won't need any of them. We only need the previous row. Now this gives us a hint that maybe we can try solving it using only 2 rows. Let us call these 2 rows as previous and current. Now current corresponds to the row that we are currently filling. We are currently trying to fill. This may correspond to some value of I here. That means it may correspond to that we are considering first I items. If current is corresponding to first I items, then what will previous correspond to? It will correspond to first I minus 1 items. And what will be the dimensions of these 2 rows? The dimensions will be the same as this. So we have noted here that the size of the 2 rows will be w plus 1. Now we understand that current row corresponds to using the first I items and the previous row corresponds to using first I minus 1 items. Now let us try to see what does every position of this row correspond to. Now any position of this row, let's say it is denoted by J. This would correspond to capacity J. So what will the value here correspond? The value here will represent the maximum value that we can obtain by considering first I items and when the knapsack's capacity is J. So now let's try to think how can we obtain our final answer. Our final answer in this 2D matrix corresponds to this position. So if we start our previous and current from row 0 and 1, then 1 and 2 and so on till current reaches n, then whatever is the last element at current, its value will be our answer. So we have noted here how will we derive our final answer. Now we can see that we will have to iterate, and in every iteration our previous and current will update. It will start from 0 and 1, then 1 and 2 and so on. Now when we move from one iteration to the next, the current row will become previous for the next iteration, and the row to which our previous was pointing, it will be of no use. For example, when we move from here 0 and 1 to 1 and 2, then we won't need 0th row at all. And when in 0 and 1 we would have filled current row as row 1, then this row will act as previous for 1 and 2. That means at the end of every iteration, our previous will point to the current row, and in every iteration we will be filling a new current row. Now let us see how will we fill this current row. That means let us try to see how will we fill value at any particular position j. Now as per this recursive relation, the value at this I comma j will depend on the value at I minus 1 comma j minus last element weight. So value at I minus 1 means it will lie in previous row, and j minus last element weight means it will lie in a prior column. So maybe this lies here, and it will also depend on I minus 1 comma j. Again I minus 1 means it will lie in the previous row, and j means the same column. So maybe this lies here. So we have the values here, right here in the previous row. So using this, we can fill the value at any position j. Great. Now we know how to fill the value at any position j. That means we know how to fill the current row. We know how to proceed in every iteration by updating previous and current. And we know how will we find our final answer. What we don't know is how do we begin. Initially, our previous and current will point to row 0 and row 1. Previous pointing to row 0 means I is equal to 0. That is our base condition. And for the base condition, we know that the maximum value obtained is 0. So initially, the value of the previous array will be all zeros. And in every iteration, we will have a new current array. The first element of the new current array will always be 0, because the first element corresponds to capacity is equal to 0. And for capacity equal to 0, this is our base case, we know that the maximum value obtained is 0. So now we know how to start filling up the previous and current rows. We know how to update previous and current rows in every iteration. We know how to fill the value for current row elements at anywhere. And we know how to derive our final answer as we fill previous and current rows. That means we have everything that we need to formalize our thoughts into algorithm. So let's try doing that. It is clear that we need a previous array of size w plus 1, and we have to fill it with zeros initially because this corresponds to the row 0 of the matrix. Then we have to iterate from I is equal to 1 till I is equal to n, because now we will be filling a current row at every I.
Since in every iteration we will be filling a new current row, we declare a new current row here with size w plus 1, and we assign its first element's value as 0 because this corresponds to this base condition. Next, our aim is to fill this current row as a whole. To fill this current row, we again have to iterate. Now we are trying to fill the value at current j. What does current j correspond to? That means j is the capacity for which we have to fill, and current row itself corresponds to first I elements being considered. So in current j, we have to fill what is the maximum value that we can achieve by using first I characters with capacity of knapsack being j. To fill that, we need the include answer and the exclude answer. So first we go on to calculate the include answer. To calculate the include answer, we need these two things, last element's value and last element's weight. Now since we are considering first I characters, last element will lie at index I minus 1. So we have the last element's value and last element's weight from val and weight array. Next, including the last element makes sense only if the capacity of the knapsack is greater than the weight of the last element. So we add this condition that the capacity of the knapsack should be greater than or equal to the last element's weight. Now if this condition is satisfied and we include the last element, what is the include answer? The include answer will be the value of the last element plus the answer for this problem. That is, we have to maximize the value that we can obtain by using first I minus 1 elements because we have already included the last element and with this reduced capacity. Now we are talking about first I minus 1 elements. So where will the value for the first I minus 1 elements lie? It will lie in the previous array. So in the previous array at this index we will find the value that we need. So we add to the last element value the value previous of j minus last element's weight. And if this condition was not satisfied, then the maximum value that we can obtain by including the last element is 0 because there is no point in including the last element. Now we have calculated the include answer. Now we need to calculate the answer for the exclude case when we don't include the last element at all. When we don't include the last element, the value that we can obtain is equivalent to the value that we can obtain by using only first I minus 1 elements and our capacity of the knapsack being same as j. Now since we are talking about first I minus 1 elements, where will this value lie? This will lie in previous array as current corresponds to I. So, and in previous array it will lie at index j. So this way we will have exclude answer as well. Now we have include answer and we have exclude answer. So we can fill the value at current j. It will be maximum of the two. Once we have filled current row in this manner for all j's, what do we need to do? We need to move to the next iteration. And in the next iteration, this current will become previous. So here we add this statement that previous now points to current. And in this manner, we will keep on filling previous and current rows. And at the end of this final iteration, our current and previous will point to the same last row, and the last element of it will be our answer. So we return previous W as our answer. So this completes the space optimized version of bottom-up algorithm for the knapsack problem. Now what will be the time and space complexity for this algorithm? Time complexity will be big O of n into W because we are figuring out answer for every combination of n and W. The space complexity will be big O of W because we are only using two rows of size order of W, previous and current. Now one may think that here in every iteration we are initializing a new current array. We are declaring a new current array. So shouldn't the space complexity be equal to big O of n into W? No, that's not the case. Why?
Let's see what happens when we declare this previous array. A new memory block is allocated and a pointer previous points to this memory block. Now as we come to this iteration, we allocate a new memory block for current as well. So at this point, a new memory block for current is also allocated and current points here. Now as we go through this logic, we keep on filling the values of current array. At this stage, we point our previous to current. Let's see what happens here. Now our previous pointer also points to this memory location, and the memory location to which it was previously pointing, this connection no longer exists. So now on this memory location, no pointer exists which is pointing to it. Therefore, there is no way that our program can now reach this memory location. So whatever is the garbage collection mechanism of the language we are using, that garbage collection mechanism will free up this memory. And when we move to the next iteration, here we will again declare a new current array. This means another memory block will be allocated and our current will point to this memory block. Now our current will not point to this memory block and only previous will be pointing here. So this way we will only have 2 rows at max and memory will keep freeing up for one of the rows. And therefore the space complexity is big O of W and not more.
Let us now go through the working code for the algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function. It takes as input n, the number of items, w, the capacity of the knapsack, and the weights and values of those n items. And it is supposed to return the maximum value that we can take in this knapsack with the constraint of that the capacity of the knapsack is w. So first of all, we declare a previous array of size w plus 1. Then we first fill it with zeros because it first corresponds to I is equal to 0. I is equal to 0 means that we are considering first 0 items. That means we are not considering any items. And if we are not considering any items, then the maximum value that we can make in the knapsack is 0. So we fill this previous row with 0 at all positions. Then we need to iterate from I is equal to 1 till I is equal to n. And in every iteration, we have to fill a current row. We have to fill this current row with the help of a previous row. So since we need to fill a current row in every iteration, we first declare a new current row. We put the first element's value in this row as 0 because the first element in current row corresponds to j is equal to 0. J is equal to 0 means the capacity of the knapsack is 0. And if the capacity of the knapsack is 0, then the maximum value that we can make in the knapsack is 0. So we put this first element as 0. Next, our aim is to fill this current array in full. To fill the current array, we will have to iterate. We will have to iterate from j is equal to 1 till j is equal to w. Then, to fill the value at any position, current j, we need the values of these two things, the last element's weight and the last element's value. Now, since we are considering first I items at this stage, therefore, the last element, the last item lies at the index I minus 1. So we get the values for these two things. Then we need to calculate the answer for our include case. That means we need to calculate the maximum value that we can make in the knapsack if we include the last item. So to calculate that, it makes sense only if the capacity of the knapsack is greater than or equal to the weight of the last element. So we put this condition. And if this condition is satisfied, then what is the value that we can make, maximum value that we can make in the knapsack? The maximum value that we can make in the knapsack will be equal to the value of the last item plus something. Why do we need to include the value of the last item? Because we have included the last item. What will be this something? This something will be the maximum value that we can make by considering only first I minus 1 items and with the remaining capacity of the knapsack. Why first I minus 1 items? Because we have already picked the ith item. And what will be the remaining capacity? The remaining capacity will be j minus the weight of the last element. Now since we are talking about first I minus 1 items, its answer will lie in the previous row because the current row corresponds to considering first I items. So this way we can compute the include case answer. And if this condition was not satisfied, then our include case answer will be 0. Similarly, we have to calculate the exclude case answer. Exclude case answer means the maximum value that we can take in the knapsack if we have decided that we won't take the last item at all. That means we have to form the maximum value using first I minus 1 items. So where will this lie? This will again lie in previous row. And what is the capacity? The capacity is j. So the exclude answer will be previous of j. So what will be our final answer for current j? It will be the maximum of include and exclude answer. So this way in the iterations we can fill this current row. Once we are done with filling the current row, we have to move to the next iteration. In the next iteration, there will be a new current row and our previous will point to this current row. So we point our previous to current here. And similarly, we can iterate till I is equal to n. And once we are done with all the iterations, our final answer will lie at the last element of the last current and previous will also be pointing to that. So we will return previous W as the answer. So this completes the code for the space optimized approach for bottom-up dynamic programming for knapsack problem. Let us now see our code in action. So we are supplying as input one test case. In that one test case, we will have 3 items. The capacity is 2. The values of the 3 items are 10, 20 and 30. The weights of the 3 items are 1, 1 and 1. Let us see what is the maximum value we can take with this capacity in the knapsack. It is 50 because of 20 and 30.
There could be a further extension to this problem. In the previous solution, we had optimized our space complexity to big O of W, but we were using 2 rows or 2 arrays. We could be asked as an extension to solve this problem using only one array. How will we do that? Now, in the previous solution, we have been filling this current row. So we needed this current row. And to fill the values at this current row, we needed values from the previous row. And that is why we needed the 2 arrays. Now let us say that we have to fill this current array. That means we need at least one array, the current one. Let us see if we can do away with the need for the previous array. Now, in the previous solution, what used to happen was current array was empty initially, and using these 2 values, we filled the value here. So this was the manner in which we were filling the current array previously. And this was going through the iterations from one iteration to next. Now let us see how can we eliminate the use of these 2 things and put the values of these 2 things in this array itself. Consider this one. This one is the same column as the current column that we are trying to fill. Now in the previous solution, this array was empty. What if this could be just the previous value of this current array? That means in the new solution, current array is not empty, but it contains the values from here. All the values of previous are there in this current array. Then we know that this value is already lying here and we need to update it. Similarly, the value present here will be lying here. Now, to fill the value at this position, we need these 2. This one is present as old value at the same position. So we already have that. What about this one? this one was present here as old value at this position. But as we would have filled this current array, this one would have been updated to its new value. So we would have lost the old value here. So what do we do? How do we keep this old value and use this to fill here? Instead of traversing this array from left to right, if we traverse from right to left, then when we reach here, this position will still hold the old value, and this position will also hold the old value. So we have both the values to derive the final answer here, and we can fill this here. So that means we can probably solve this using one array. Now let us try to formalize our thoughts into algorithm. So clearly we need one array current of size w plus 1. We will initially fill it with zeros as we did with the previous array in previous solution. Once we have filled this with 0, we have to iterate for all i's. So we will iterate for all i's from 1 to n. Now at this point, in every iteration, we will have some values filled in this current row, but these would be corresponding to the values at I minus 1. So what is our aim in every iteration? In every iteration, our aim is to update the values of current row from old values to new values. Old values that corresponded to I minus 1 and new values that should correspond to I. To do this, we have to traverse the current array. Now, as discussed, we will traverse from right to left. That means our j will range from j is equal to w till j is equal to 0. Now, the updated value or the new value at this position will be maximum of the two. This value is already filled here. So we need to update if this is a valid index to go to. That means the capacity of the knapsack that we are dealing with is greater than the weight of the last item. So if this is a valid index to go to and this value is greater than what is the current value here, then we will include that, because as we notice very carefully, this is the exclude case answer and this is the include case answer. So we put here this condition that if the capacity of knapsack is greater than or equal to the last element's weight, then what will be the value, updated value at current j? It will be maximum of the two. First thing, the old value at current j. Old value corresponds to the exclude case, or the new value can be last element's value plus current of j minus last element weight. This is the include case answer. So if this is greater, our current j will be updated. And in this manner, we can fill current j for every j. And in this manner, we can fill the current row and we can update it for every I. So finally, when we are done with all the iterations, its last element would correspond to our answer. So this is the algorithm that solves the knapsack problem in just one single array.
This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.